Hi, my name is George Wenson, and my research was done with Dr. Lisa Klein on hydrophobic surfaces capable of condensing water. So this research seeks to answer the problem of freshwater insecurity around the world through a technique known as fog collection. Fog collection is the condensation and transportation of water onto a substrate or surface with hydrophobic properties. So a little bit of background information. The hydrophobicity of a surface is found by looking at a water droplet's contact angle. The contact angle is the angle that the surface of the water droplet makes with the surface. Rough surfaces actually contribute to hydrophobicity of the surface. So there are two states that describe a water droplet onto a rough surface. The first state being the Wenzel state, and the second state being the Cassie-Baxter state. The Wenzel state describes when a water droplet gets water in between the ridges of the surface, and the Cassie-Baxter state describes when water actually rides on top of the ridges on the surface. So how did we accomplish our analysis in this research? We used several surface energy models. So the main model used in this research is the equation for capillary filling, which is this first equation right here. Z refers to the wall height, R is the width of channels, eta is the viscosity of the water, which is dependent on the temperature of the water, sigma is the surface energy of the surface, and theta is the contact angle of the water droplets. So a higher dZdt means that more water can be collected per unit time. So to gain a rough idea of how much water will be collected over a certain amount of time, the above equation was integrated to give this next equation right here. And what we tried to do was find different kinds of trends that are present inside of this equation to see what it might tell us about the surface. So what did we get from our analysis? From the equations, it was seen that by increasing the contact angle, the wall height actually decreased. However, the relative loss in wall height for every rise in the contact angle got smaller and smaller. It was also found that by increasing the channel width, the wall height of the substrate also increased. However, for every increase in channel width, the corresponding increase in channel height became smaller and smaller. It was also determined that the viscosity of the water played a very important role in how much water was collected. So higher temperature water, which has a lower viscosity, was able to be collected much more, which is a very important finding because it downplays the role that this surface needs to play as a heat sink. And also a very expected finding was that the more time that the surface was allowed to collect water, the more water could collect. So from this, it was concluded that the optimal surface suggested by the models used in this research was a surface with 1 millimeter ridges, a wall height of 1 millimeter, and a contact angle of 70 degrees. This function also suggests that the optimal aspect ratio tends towards an aspect ratio of 1 just because of the relationship between ridge width and wall height. The next step in this research will be to put the theoretical findings of the study into practice in a lab to determine the accuracy of the theoretical model and see if it holds, and if not, why doesn't it hold? Also performing surface modifications to change the material in contact with the water. I would like to thank Dr. Lisa Klein for guiding me through this research and the RESTI Research Assistant Program for making this research possible. Thank you very much.